You're standing on the deck of a small wooden vessel somewhere in the open Pacific, thousands of kilometers from the nearest land in any direction. There's no coastline in sight, no landmark, nothing but water stretching to the horizon in every direction you turn. And yet the person steering this vessel isn't lost. They know exactly where they are, exactly which direction to hold, and roughly how many days remain before land appears. They have no compass, no map, no satellite signal. What they have is the sky. This is the story of how humans learned to read the stars well enough to cross oceans with nothing but their eyes and their memory, and why that skill might be one of the most underrated feats of engineering our species ever pulled off, using nothing but the night itself as the instrument. Let's start with why this problem was so difficult in the first place. The ocean has no fixed features, no mountains, no rivers, no trees to mark a route. Every wave looks like the last one. Drift a single degree off course over a journey of 1,000 kilometers, and you miss your destination entirely, with nothing around you but open water in every direction. For most of human history, this made long-distance sea travel functionally impossible beyond sight of the coastline. And yet, roughly 3,000 years ago, Pacific Islander populations began deliberately sailing out into open ocean, not drifting accidentally, but navigating with intention towards specific, previously identified islands separated by hundreds or even thousands of kilometers of featureless water. Genetic and linguistic evidence backs up just how deliberate this expansion actually was. Studies tracing the ancestry of Pacific populations show a clear, staged migration pattern moving outward from Southeast Asia and near Oceania into the remote Pacific over roughly 2,000 years, reaching islands as distant as Hawaii, Rapa Nui, and Aotearoa, New Zealand, some separated from their nearest neighbors by well over 3,000 kilometers of open ocean. This wasn't random drift carrying a handful of survivors to scattered shores. The pattern shows repeated, successful two-way voyaging, colonizing canoes carrying enough people, crops, and livestock to found permanent settlements, then in many cases returning home to guide further expeditions. That kind of repeatable back-and-forth accuracy is only possible with a genuinely reliable navigation system, not luck stretched across multiple generations of separate accidents. Here's the part that should genuinely surprise you. They weren't guessing. Traditional Pacific navigators developed a system now referred to by researchers as a star compass, a mental model dividing the horizon into distinct zones, each one marked by the rising or setting point of a specific star or constellation. Because Earth's rotation carries stars across the sky in predictable, repeating paths, a star that rises at a certain point on the horizon tonight will rise at that same point again tomorrow night, and the night after that, for the entire navigable season. Memorize enough of these rising and setting points, and you have something close to a rotating clock face fixed to the sky itself, one that never needs winding and never runs out of batteries. A single star is only useful for a few hours before it climbs too high overhead to give a reliable bearing. So navigators memorized entire sequences, one star handing off to the next as the night progressed, sometimes tracking more than a dozen different stars across a single night's voyage. This required an extraordinary feat of memorization, not of names in the way we might memorize constellations for fun, but of relative position, timing, and how each star's path shifted slightly depending on the latitude the voyage was crossing. Some navigational traditions organized this knowledge into memorized chants and songs, embedding star positions, wave patterns, and known island locations into rhythmic verbal structures that could be passed from a master navigator to an apprentice without ever being written down. This mental star compass wasn't a rough approximation either. Researchers who have studied surviving practitioners of the tradition describe systems dividing the horizon into as many as 32 distinct houses, each one anchored to a specific star's rising or setting point, functioning with a level of precision that rivals a modern compass rose. An apprentice navigator might spend a decade or more under direct instruction before being trusted to guide a voyage alone, memorizing not just star positions, but the specific sequence in which stars needed to be checked and cross-referenced throughout an entire multi-night crossing, since clouds could obscure any single star at any given moment and a backup was always needed. Stars alone weren't the whole system. Skilled navigators also read ocean swells, the long rolling patterns of waves generated by distant, persistent winds far beyond the horizon. Unlike the choppy, chaotic surface waves created by local weather, deep ocean swells travel in remarkably consistent directions over enormous distances, sometimes originating from storm systems thousands of kilometers away. A trained navigator lying in the hull of a canoe could feel the rhythm of these swells through the motion of the vessel itself, using them to hold a steady bearing even on a heavily overcast night when no stars were visible at all. Some traditions developed physical stick charts, woven frameworks of wood and shell, used to represent swell patterns and island positions, not carried during actual voyages, but used on land to teach apprentices the underlying wave geography of the surrounding ocean before they ever set sail. Birds mattered too. Certain seabird species reliably fly out from land each morning to feed and return each evening to roost, meaning their flight paths at dawn and dusk could reveal the direction of the nearest island long before it became visible from the water. Cloud formations offered another clue, since islands often generate distinctive stationary cloud patterns as warm air rises off the land, visible from far greater distances than the island itself. Even the color of the water and the behavior of phosphorescent plankton at night were read as clues by some traditions, since certain currents and shallow reef systems produced faint underwater light patterns that experienced navigators learned to recognize on sight. A skilled navigator was reading an enormous layered dataset simultaneously: star positions, swell direction, wind shifts, cloud shapes, bird behavior, and water conditions, cross-referencing all of it continuously throughout a voyage that could last for weeks. This wasn't unique to the Pacific. Arab and Indian Ocean sailors developed their own star-based navigation systems centuries before European vessels attempted similar open-water crossings, using instruments like the kamal, a simple handheld wooden card threaded onto a knotted string, held at arm's length and used to measure a star's angle above the horizon. Each knot on the string corresponded to the correct viewing distance for a specific latitude, meaning a sailor could hold the same reference star, adjust the string to the correct knot, and know with real confidence whether the ship had drifted north or south of its intended course, all without a single written calculation. Norse sailors crossing the North Atlantic relied on a combination of star positions, sun angle, and even the flight patterns of shorebirds carried aboard specifically to be released and followed toward the nearest land when visibility was poor. Polynesian and Micronesian traditions, Arab dead-reckoning navigation, Norse open-water sailing, and later European celestial navigation all independently arrived at a shared underlying insight: that the night sky, precisely because it is so consistent and predictable, could function as a reliable positioning system, centuries before anyone had a word for satellites. What's remarkable is how this knowledge survived at all. None of it was written down in the earliest Pacific traditions. It lived entirely in trained memory, passed from master navigators to selected apprentices through years of direct instruction, repeated voyages, and rigorous oral transmission. Losing a master navigator before their knowledge had been fully passed on could mean losing centuries of accumulated positional data permanently, which is precisely what very nearly happened. By the mid-20th century, traditional wayfinding knowledge across much of the Pacific had faded dramatically, disrupted by colonization, missionary suppression of indigenous practices, and the arrival of modern instruments that made the old skills seem unnecessary. Entire island communities that had once produced generations of trained navigators found themselves with no one left who held the complete system. The near loss of this knowledge is itself part of the story. In the 1970s, a Micronesian navigator named Mau Piailug, one of the last people alive still trained in the traditional system, worked with researchers and a new generation of Pacific Islander sailors to revive and document wayfinding techniques that were on the verge of disappearing entirely. Piailug successfully guided a voyaging canoe called the Hokulea across more than 3,000 kilometers of open Pacific, using nothing but traditional star, swell, and bird navigation, no instruments at all, proving definitively that the ancient system still worked exactly as it always had. That single voyage helped trigger a broader cultural revival across Hawaii and the wider Pacific, with new generations training in a navigation system that had almost vanished within living memory and modern. Voyaging societies now actively teach the technique in dedicated schools specifically to ensure it is never lost again. Zoom out, and the deeper point becomes clear. Long before anyone had a written alphabet, a magnetic compass, or any mechanical instrument whatsoever, human beings had already solved one of the hardest positioning problems imaginable: tracking a moving position across a featureless, ever-shifting surface, using nothing but a memorized model of the sky and the patient testing of every generation before them. Every satellite orbiting overhead today, every GPS signal your phone quietly receives, is a direct descendant of that same basic idea. The sky holds fixed, predictable information if you know precisely how to read it. The instruments changed completely, from memorized star houses and knotted string to orbiting hardware bouncing signals back to Earth in fractions of a second. The underlying insight never really did.